Okay, so we're gonna show you this. This just helps you really solidify the image of what's going on. Okay, so we've got this. This is our 8.5. It's 8.5 by 11, right? So that's I can adjust the length and width of this original sheet. So 8.5 by 11. And what are we going to do? We are going to decide how big of a cutout we're going to show. Okay, and so we did 1.5, maybe that's something like this, but we got our choice. And once we pick a length of a cutout, all four corners are cut out with the same square, same size square, based on that cutout length. All right, so then we cut them out. And that, when we cut out those squares and discard them, it results in these four flaps. And then we fold up the flaps and create a box with an open top. So if there was any doubt what we were talking about, hopefully that's all gone now. Make perfect sense? All right, cool. So so here's another kind of view of that, where I can just view we can view the size of the cut and kind of the resulting box as I change the size of the cut like that. Okay, so you guys were telling me about constant and changing quantities in this situation. So what is let's start with some constant quantities. So constant quantities Okay, what is a constant quantity in this situation? Okay, so the length of the original sheet. Okay, what's another constant quantity? The what? The base's side. So which width are you talking about?
The 8.5.
Okay, so that's the width of the original sheet. What else is constant? Yeah.
The area of the
Yep, area. Did you think of any other constant quantities in this situation? Those are the main ones. There might be others, but anyone think of another one? All right, so that's good. We should know that, but really what we're focused here on is the changing quantities. That's what makes things interesting. So let's list those out. What are some of the changing quantities in this situation? Someone? Cutout length, square cutout length. Or square cutout side length. Others. What else changes? Other quantities change. The height of the box. Is it okay that we're not putting units on these? Why not? Because we're not. When do we need units? Variables, because those variables actually take on numbers, and we got to know the meanings of those numbers. That's what units specifies, what the meanings of those numbers are. But if we're just saying the height of the box, we're just saying from here to here, right? It's that attribute of the box. So we don't need units unless we're actually starting to apply numbers, which is our variables. Okay, other changing quantity. Volume of the box. What else? Length of the box, width of the box. How about one more changing quantity? What's that? The perimeter of, like the around the top? Yeah, so the perimeter of the box around the top, say. So around the top edge, say. Okay. Cool. So let's. What we're interested in here is we're going to call the square cutout side length. That's going to be our variable x. So we're going to say x equals the square cutout side length. How did I do defining that variable? Okay, so now x is taking on numbers. So if x takes on numbers, we have to specify the unit, because if it's 2, we don't know what is 2 what? 2 feet, 2 inches, right? So square cutout side length in inches. Okay, and we're going to be focused on that, and we're going to call L the length of the box in inches. W the width of the box in inches. And V the volume of the box in inches. In inches? Cubic inches, right? Cubic inches. Or inches cubed. Okay, so you guys did an example for a square cutout length of 1.5. So now we're just going to do it generally. Okay, so here's our width of the box. Where does that show up in the picture at left? So where in this picture do you see is W seen or represented? What's that? Okay, so is it, he said the dotted line or the flap. So from here to here? Yep, that's it. So this is the width of the box right here. From there to there. And how can we write that width in terms of x? How can we write W as a formula in terms of x? Okay, everyone do it. So given x here like this, so this is actually x right here, right? What is W in terms of x? Do I know any names yet? Is it Benji? Did you get W in terms of x? No. Do you have any thoughts about that? So given what x is, how could we calculate what W is? What would you do? What's that? Okay, he says has to do something with 2x. So does W equal 2x? Yeah. But 2x is important, right? Yeah. So the original width, or the fixed width of the original piece of paper was 8.5. So you're saying? 8.5 minus 2x. Agree with him? Yeah, because the original width is 8.5. We take off part of that X amount on the left, X amount on the right, and we're left with then the width of the box. Okay, what about the length? So the length is here. How does it show up in the other diagram, the flat sheet? Can you describe how the length shows up here in the flat sheet before it gets folded? Which dotted line? Yeah, like the vertical dotted line, right? So the vertical dotted line. And how long is that? How long is the length of the resulting box? Yeah, so same thing. We're going to have start with 11. That's our 11-inch piece of paper. And we're going to take off X like here, say. And take off another X down here. So then the resulting length is going to be 11 minus 2X. All right, now we're ready to build a formula for the volume. So the volume then, you told me, was length times width times height. Okay, so what is the length? Width. And the last thing was the height of the box. What was the height of the box? Right, so imagine this flipping up, and that's going to be your height right there. Whatever you cut the side of the square to be, when you flip it up, that's going to be your height. Okay, so this is a formula for volume in terms of X, for any X. In terms of X, right? Volume in terms of X. Yep. So let's just quickly talk about X. What is the smallest? So the question is, does any X value work? Does any X value work in this situation? Can we just pick any real number X? So let's determine which ones are possible. So what's the lowest possible value of X that you could have? So does it make sense to have X equals 0? Is it physically possible? Does it work? Because what? So can we cut out a square with side length 0?
The smallest number that we can have is X is greater than, or I guess it's 4.25.
Smallest number of X? We're talking about the smallest number of X that we could have.
Yeah, because it can't be larger when you multiply by 2. It can't be larger than 8.5. So whatever half of 8.5 is, it can't be.
No, we're talking about the smallest. You're talking about the largest value of X. We're talking about the smallest value of X. How big of a cutout we could make. So I think you're thinking about the biggest value of X.
X
Yeah. Oh, go ahead, sorry.
X has to be greater than 0.
Greater than 0. Never approaches 0. So that's what he's saying, strictly greater than 0. So here's the deal. Is it physically possible to have X equals 0 in the real world? Yes. Yes. Okay. Let me show you. Anyone got a piece of paper? Andy? You ready? I'm going to cut out squares of length 0. Ready? I just did it. Okay? It's possible. Can I cut out a square length of -1? -1/2? That's impossible. That's impossible. But 0 is physically possible. It's a valid value for X that results in a real world situation that's valid. Then, okay, I'm going to fold up, now I just cut off the squares, now I'm going to fold up the flaps, and there's my box. All right? What's my volume? 0, right? So it feels a little uncomfortable because we don't really get a box. But you want to include all values that just are possible, that are actually valid in the real world. Even though we don't get a box, x can still be 0. It's okay. It's just a flat sheet of paper with no squares and no box and a 0 volume, right? A 0 volume. Okay, so x equals 0 is okay. What about the greatest value of x? So here I can, so where I'm still okay, right? I'm still okay, and I'm going to run into difficulty. What's the length of the cutout here? What's x here for this situation that I moved the thing to? Yeah, so haven't I just cut squares out of the width so that it's all gone? So here x is 4.25. And then we just get 2 flaps, and or you look over here on the right, you just fold them up and it's just a flat vertical sheet. Physically possible? So yeah, you don't get a box that you can put stuff in. But it is a physically possible situation. So this is for x equals what? 4.25. So what about x equals 4.5? Can we do it? So if I come over here and I cut out 4.5, this, can I now cut out a square of size 4.5 up here? No, I ran out of room, so this is less than 4.5, so I can't do it. But 4.25 is possible. That's the largest. That's what I think you were talking about, right? So that's the largest value of x that I can do. Again, I don't get a box, but I can physically do it in the real world. So we let x be that be a valid value of x. Okay. So our x values can go from 0 to 4.25. Of course, the boxes that are usable and relevant are for x values between those two. But we do include 0 and 4.25. So you can say that like this. Less than or equal to. Or you can use square brackets. Those both say the same thing. X from 0 to 4.25 inclusive, including the ends. Okay, so let's look at. We're going to look at the this length relationship a little more closely and the volume relationship a little more closely here. Okay, so I'm going to graph the length of the resulting box in inches in terms of the cutout side length. So I'm going to put my cutout side length on the horizontal axis, and I'm going to put my the length of the resulting box in inches on the vertical axis. And so here we are at x equals 0. So the blue arrow, and then you're going to see on the cutouts, it's actually going to show it as blue. So that length is blue in the cutouts. So x equals 0 results in a length of what? The length of the resulting box of what? So it's that. Okay, so cutout length of 0. Length of the resulting box is 11, right? So it's going to give us this point right here. So we get that point right there. Okay, here's what I'm going to do. So now I'm going to let the cutout length increase by 0.5. How can I show that on the graph? How can I show just, here I am, the cutout length is 0, the length of the box is 11, and I want to show an increase of the cutout length in point as 0.5. How can I do that? Horizontal line, right? So we've done this before. So kind of short, so right like that. Okay, and the length of that is? I said 0.5. And how can we represent that symbolically? So what is our symbols to represent increasing the cutout side length by 0.5? What's our symbols for that? Tell me your name right here. No. Yeah. Tyler.
You can do like delta L.
Is it delta L? I'm increasing the cutout side length by 0.5. You want delta X? Delta X. That's delta X equals 0.5. Okay, so we're going to make a table of this, of delta X and delta L. And so our first one there was that we said X goes from 0 to 0.5. And so what was delta X? 0.5. So when we do that, how much does L change? That's the question. How much does L change? Okay, I heard 1 and I heard -1. So let's do it. Here we go. Ready? I'm going to increase by 0.5. Almost. It's touchy. There we go. Okay, so I just increased by 0.5. How much did L change? -1, right? Because if we took off a half on each side, we started at 11. We took off a half on each side, then we took off a total of 1. And how can I show that on the graph? Vertical line going down. So vertical line goes down, and that's our delta L of 1, -1. Okay, I'm going to do it again. I'm going to go X from 0.5 to 1. Okay, what is delta X going to be? Same thing, 0.5. Here we go, watch, ready? Starts there and goes to, so delta X was 0.5. Again, I can show that horizontal line, delta X of 0.5. How much was delta L? If I take another half off each end, off two ends, then it's good. Every time I take a half off, the whole length of that resulting box is going to do what? Go down by 1. All right, let's do X from 1 to 2. So delta X is going to be, what's our delta X? 1. Here we go, ready? So we're going to go from 1 to 2. Watch it. Here we go. 1, 2, 2. So our delta X was +1, delta L. Now I'm taking 1 off each side. So the result, the length of the box goes down by 2. Finally, let's do one more. Do 1.5. So we're going to go from X goes from 2 to 3.5. You do all the rest. So from 2 to 3.5, delta X is 1.5. Delta L, -3. Let me show it. Here we go. So I'm going to go from 2 to maybe 3 point. That's close enough. 3.5. So our delta X was, boom, delta X was 1.5. Resulting delta L, Okay, again, you can watch this and be like, oh God, this is so easy, you know, like makes perfect sense. But can you just be given can you just be given a paragraph and a problem with some just initial information? Can you do an analysis like this? Can you come up with this? That's the real question. Because if you can, it means you really understand what's going on. All right? So, so now thinking about how L and X are changing together. How L and X are changing together. What's going on here? Let's kind of summarize what's happening. All right, why? So someone said constant rate of change. Who's that? So why?
Because equal changes in X result in consistent changes in L.
All right, so that was one of our perspectives on constant rate, right? Equal changes in X. Where did we see that? In the first two, right? Here's a change to X of 0.5. Here's another change to X of 0.5. And what was the resulting change in L? -1 both times. So equal changes in X result in consistent changes in Y. Or in this case, consistent changes in L. Okay, so somebody else, what was another perspective on constant rate, and how do you see it at work here? Somebody new. What's your name in the group? Yes.
Sarah,
Sarah.
changes in X are proportional to changes in L.
Okay, and so actually, we say we do the other way normally. So that's true. That is a true statement. No, that's true. That's a true statement. But so when we have in terms of the constant rate, we look at the vertical quantity first, and so changes in what would it be? Changes in L. But she was saying you're proportional, right? So change in L over change in X is? What would that be? So in the table, does that ratio stay the same looking at the table? -1 over 0.5, -2 over 1, -3 over 1.5. Does that ratio maintain a constant? Yeah, and the constant is? -2. Right? So the amount that the length changes is always a decrease of twice the amount that we cut off. Right? If we cut off one more on each side, then the length is going to go down by twice as much, whatever amount we cut off. All right, what was the third perspective? Someone over here. What was your name? Yeah. Jessica? So what's our third perspective? A constant rate. Oh, this one's the ratio, right? So the ratio of changes in L to changes in X are a constant. So remember what the third one was? What's your name again? What's that? You don't remember. Okay? Yes, sir. Constant multiple. So tell me in this situation what that's about.
You multiply the change in X by -2.
Yeah.
In this case,
Yeah.
and then we'll get the change in L.
Whatever your change in X is, you can also always multiply it by the constant multiple, and it'll give you the change in ln. What is that constant multiple?
2.
-2, right? So the change in L will always be -2 times the change in X. That's what we're seeing in the table. No matter what change in X we have, multiply by -2, you get the corresponding change in L. So remember in constant rate of change, the value of the constant ratio is the value of the constant multiple, right? So the value of the constant ratio, -2, is what you multiply changes in your independent quantity by to get the change in the dependent quantity. Okay, let's look at the same thing for the volume. Where's our volume? So I got similar deal here, and now we're going to do the side cutout length and volume. So make our little table over here. Now this is going to take a little more work because our volume formula is a little more complicated. So here we're going to do a change of X from, say, 0.5 to 1. What's the corresponding change in x? What change in x am I doing there? If I go from 0.5 to 1, my change in x is 0.5. And what was our volume formula? 7 minus 2x. 8.5 minus 2x times x. Find the corresponding change in v. Go. So you got it. We're going to go from 0.5 to 1, and we're going to find the corresponding change in v. So you just take 0.5 and you plug it into that formula, right? Just take 0.5, plug it into that formula, it'll give you the corresponding change in v, right? Some are saying yes, some are saying no.
Yes.
Okay, why no?
Because that's just going to give you a point where 0.5 is. It's not going to tell you how much it changed.
We put the number 0.5 in that formula. What is it going to tell us? Does it tell us a change in volume or a volume? It just tells you the volume of the box when the cutout is 0.5. Is that necessarily the same as the change in volume that you'll get for this particular change in the box of 0.5?
So you take the volume first.
Okay, good. So if we want the change in volume, we need the final volume and the initial volume. We need this, I'm showing it here. So we need this initial volume here, call it V initial. And we need this final volume here where the pink arrow is, V final. We got to subtract. That is certainly different than what you would get if you plug 0.5 into the V formula, which is the volume of the box if you plug 0.5 in. Anybody got it? 21 exactly? 21 point? 22? So it's an exact value? It's a whole number? Can we get consensus? We're going to stay just a couple minutes. Can we get consensus? Exactly 21. Exactly 21.0. Okay, now we're going to do the change from 1 to 1.5. What's delta x? 0.5. So I'll do it here. Watch, I'll do it on the screen. So I'm going to go from 1 to 1.5. There's my delta x of 0.5. Here's delta v. 21 again, right? Sure doesn't look like it. See, so it looks like it's going to be less, right? Anyone got it? Again, you're going to have to plug 1.5 into the volume formula to get the final volume. You're going to have to plug 1 into the volume formula to get the initial volume. Subtract final minus initial. What do you get? 7.5? Someone else get that? Somebody else get that?
Yeah.
Cool, thank you. All right. But wait a second, I thought that equal changes in X were supposed to mean consistent changes in V. We got equal changes in X, but we don't have consistent changes in V. I thought that was supposed to happen. What's that?
It's not linear.
Okay, not linear,
Constant rate of change.
not constant rate of change. That is for constant rate of change. So the volume does not vary with constant rate of change with the cutout length. The side of the length of the side of the box does, but the volume does not. So therefore, you have consistent changes or equal changes in X don't result in consistent changes in V. Okay, so therefore, what's the graph like? Curved. And in fact, the volume starts to go down. We could do this again later, and we get a negative delta V for a delta X of 0.5. Okay, so the difference between constant rate of change, non-constant rate of change. Okay, so I posted like a half web work. You got a half, like 4 problems for web work due Wednesday. You have your written homework. It's not changed from the weekend. And then some of you have your quiz today in recitation. See you Wednesday.
Do I have to take my name since I came in?
I didn't take roll.